Hi everyone. So in the previous video we saw the embedding and positional encoding. Today we'll be looking at the masked multi-head attention. This is a very important part of the transformer architecture. We will see what this masking is. Attention, think about attention as a way for the characters in a sequence to communicate with each other. This can allow the model to focus on different part of the input sequence while making predictions. In terms of multi-head, we'll be having two heads, and think about each head as a way to process the data, so that that head will learn different relationships in that data. So let's start with head 1. Well, think about it. Maybe we can let me start with the formula that governs the attention module. Say attention query key value. It takes in query key value, which we will be computing, and it computes the softmax of query times key transpose divided by square root of d times v. Okay, this d is actually the dimension of the embedding. So in our case, our embedding dimension was 4. We will be having two heads. So 2 divided by 2 is 2, and this 2 is actually important. We'll get back to it. So let's start by computing query, key, and value. Query is computed, well, in the previous layer we got xn, and that xn had a dimension of 2 by 4 by what? By 4. This 2 is the batch size, this 2 is the block size, and this 2 is the embedding dimension. So to compute query, we're going to say xn and multiplied by w1, a linear transformation, w1 transpose. Well, the dimension of w is 2 by the embedding dimension, and this 2 is from this. Well, when we take the transpose, it is going to become a tensor of dimension 4 by 2. So we are essentially transforming xn from a dimension of 4 to dimension of 2 by 4 by 4. This is the dimension of xn, and the output dimension is a tensor of something like this. Sorry, I'm using the wrong pen. 2 by 4 by 2. Okay, so far so good. We're going to be doing the same for key. So key is, we're going to take an xn multiplied by a separate w2 with the same dimension. Sorry, this is key. Okay, remember, these are all tensors. This has a dimension of 2 by 4 by 4. This has a dimension of 2 by 4, but after taking the transpose, it becomes 2 by 4. Okay, this is 2 by 4 by 2. So notice our data, we are transforming data from dimension of 4 to dimension of 2. Let's compute v. V is the same thing. Essentially we're repeating the same thing, but the only difference is W. Here we're using W1, here W2, here W3. So well, xn is 2 by 4 by 4, and W3 is 4 by 2, and that results in a tensor of 2 by 4 by 2. Okay, now we are done with this computation. Now we need to compute query times key. Well, query times key transpose, and this is transpose, is something like this. Query 2 by 4 by 2, dimension of query. Remember, this is batch size, this is block size, and these two came from these two that we computed here. This has a dimension of 2 by 4. After taking the transpose, it's become 2 by 4. So this is the resulting tensor, 2 by 4 by 2 dimension. We need to divide it by the square root of 4, square root of our embedding. Well, you might be asking, why are we doing this division? Well, think about it. The softmax takes in this output, this computation. And if we do not do that division, we might end up with a probability distribution, which is the output of the softmax, that is very peaky, meaning that some values can be really high, some probabilities can be, let's say, 0.99, while others are really small. So that's why we're doing this division, and that division will not change the dimension. Well, before applying the softmax, we need to apply masking. So let's see what masking, and let's take a simple example. Let's say we have a tensor of dimension 3 by 3, just a simple example. Well, in this mass multi-head attention, we really don't want tokens or characters to be looking at future tokens. We do not want any information leakage, so we don't want this token to be attending to future tokens, only the past. That is why we're applying this masking, and the way to do it is we look at kind of the upper triangle and make it minus infinity. So when we take the softmax, the negative infinities, softmax of negative infinity, I mean a large negative number, will be 0. Okay, so essentially this masking is a way to prevent information leakage. We don't want tokens to be attending or to be looking at future tokens, only the past. Okay, I hope that is clear. So we're going to take this and apply that masking. After the masking, then we will apply a softmax. Well, both softmax and masking will not change our dimension of that 2 by 2 by 4. Okay. Remember, the output of the softmax is a probability distribution. So what we need to do is take this output and multiply it by V. Well, that output 2 by 4 by 2, V has a dimension of 2 by 4 by 2, isn't it? 2 by 4 by 2. So this is 4. We'll end up with a tensor of 2 by 4 by 2. Well, this is really like kind of the output of of head 1. The output of head 2 will also have this same dimension, and we'll be concatenating this output of head 1 and output of head 2 to get a tensor of 2 by 4 by 4, which is the same as the input dimension. Okay, I hope that is clear. So I'm going to call this, let's call this output 0, or maybe output 1. So let's quickly look at head 2. Head 2 is really the same thing. We will actually be using xn, but the only difference is this w. So, and head 2 also uses this attention. So let's say query to be xn times w, well, w4, the same dimension. So xn dimension and dimension x of w4, which is the same as the dimension of w1. Okay. To get a tensor of 2 by 4 by 2. The same thing for new key, which is xn times say w, well, w4, w5 transpose. The same thing for v, xn times w6 transpose, both of which will result in a tensor of shape 2 by 4 by 2. I'll write it 2 by 4 by 2. Okay. We will then apply the masking, we'll apply softmax to end up with a tensor of the same dimension. Okay. So this is the output of head 2. Remember, these heads kind of learn different relationships in the data. So we're going to concatenate the output of head 1 and head 2. So which is really a tensor. Oh, sorry, I'm using the wrong pen. 2 by 4 by 4 after this concatenation. Okay, so far so good. Maybe we can call this, I don't know, x output. Okay, let's look at this paper. So this mask multi-head attention, the input is added to the output and then normalization. So the input of this is added to the output, and then whatever we get, we normalize it. Okay. But before that, we need to perform a projection of x0, a linear transformation x0 and w7. The dimension of w7 is embedding by embedding, 4 by 4. We're going to take the transpose, it will still be 4 by 4, 2 by 4 by 4, dimension of x0. We multiply it by w7 transpose to get a new tensor of 2 by 4 by 4. Okay. This is the output of this masked multi-head attention. So I'm going to say, well, let's say maybe x final to be xn plus, this xn that we got in, plus x output, which is this, not this, this is like the updated x output. This x output is the one here. We add them, then we perform, then we apply a layer normalization. This layer normalization, I'm not going to go deep into it, but it stabilizes learning and accelerates training. So the dimension is still going to be 2 by 4 by 4. Notice 2 is the batch size, 4 is the block size, and 4 is the embedding dimension. So we are back to the same dimension that we started, which is xn. Let's look at this. So We are done with mask multi-head attention and this addition with normalization. Well, from here we will actually be going to feed forward. Why? Because you see, this decoder depends on the output of this encoder. Well, in GPT, for example, we don't have any encoder. This kind of module depends on that output. Since we don't have it, we can just skip it and go to this feed forward, which will be seen in the next video. Thank you for watching. I hope everything is clear.